All right, so welcome back, everyone. This is the beginning of Chapter 2. So we're done with Chapter 1. We're starting Chapter 2. Chapter 2 is going to be new material. So what was going on back there in Chapter 1, that should have been a review. Now we're starting to look at new material. In Chapter 2, we're going to take a look at the idea of a limit and the properties of the limits. And so in Section 2.1, this is just an overview, a preview of what's going to happen in calculus. Okay, so we're going to take a look at what calculus is and how it compares to pre-calculus. We're going to take a look at the tangent line problem and see how that is fundamental to the development of one type of calculus, one side of calculus, and the area problem, and also how it was basic to the development of the other side, the other half of calculus. All right, so what is calculus? Calculus basically is the mathematics of change. In calculus, we address how equations and models are just equations that actually do something rather than just some random equation. It's used to predict, maybe, physical quantities. But calculus says, okay, talk to me about how things are changing. And then the applications of change vary. So when we get into the applications of change, we start talking about things like velocities, accelerations, tangent lines, slopes, areas, volumes, lengths, centroids, curvatures, and a variety of other concepts that engage science, engineering, economics, just in general real-life situations. Okay? So without calculus, back in your algebra days, you would study functions and you would be asked questions like, hey, for this function, if I told you that x was 5, what's y? Or if I told you that x was 7, what's y? Or if I told you that y was 12, what was x? And you'd work back and forth, finding static points on a curve. Now, in calculus, we start saying like, okay, well, what about if there was a hole in your graph? How could we figure out where that hole is? How could we explore the area around that hole? Over here a little bit, and maybe over here a little bit. And how could we use the knowledge of that around information to estimate or to predict where that hole actually lies? Okay? In your pre-calculus and your algebra classes, you found slopes of lines. You found slopes of many lines. Someone gave you a point over here. Someone gave you a point over here, and you said the slope of the line connecting those 2 points was the change in y divided by the change in x. But in every single situation, you always had enough knowledge to do that. And what I mean by that is, since your knowledge of slope required 2 points, you were always given 2 points. In calculus, we ask a different question. We say, hey, what's the slope of this curve? But we only give you 1 point. And so how do we find the slope of something if our knowledge of slope requires 2 points, but calculus only gives us 1 point? And so we're going to take a look at how to do that and find techniques for doing that. Essentially, though, once you have a slope of a line, you can talk about secant lines versus tangent lines. Now, you'll want to grab hold of this terminology, learn this terminology. A secant line to a curve is a line that passes through 2 distinct and known points on the curve. In fact, those 2 points are the points that are used to calculate the equation of that line. Now, the tangent line problem says something different. The tangent line problem says, what if we only knew 1 point on the curve? Could you find the equation of the line that is tangent? Okay. Now, I know what someone is thinking. Well, what if this went up further over here and then this blue line went out and crossed again? Wouldn't that make it a secant line? No. A secant line isn't just a line that crosses at 2 places. A secant line is a line that is found, or the equation of that line is found by knowing 2 points and using both points. A tangent line is a line where the equation is found by only knowing 1 point. The fact that it may or may not intersect somewhere else is irrelevant to the question. Okay? In the tangent line problem, we know this 1 point, and we're asked to find out what's going to happen. Okay? In your pre-algebra course, you found the average rates of change between 2 points in time. You were told the car is here at 2 o'clock, the car is there at 3 o'clock. What was the average rate of change? In calculus, we say, what's the instantaneous rate of change? Not over a time interval, not on an interval from A to B, but at a specific single point in time. Okay? Think of this as the policeman problem. The policeman doesn't care what your average speed is when you're driving down the highway. The policeman cares what your instantaneous speed is. How fast are you going right now when he pulls out that radar gun and shoots you with it to find out what the speed is? Okay? So it's that kind of a situation, a difference. Right? Without calculus, you may have looked at the curvature of a circle. In calculus, and this is specifically, this is going to be like Calc 2 here. So for those of you that are going on the Calc 2, you'll take a look at curvature. How curvy is a curve? And we have ways to measure the curviness, how fast it's curving. Right? In your college algebra, you found heights of curves. In calculus, one of the big things we talk about finding is maximums and minimums. Find the highest point and find the lowest point on a curve. Right? When you get into Calc 3 and you start talking about three-dimensional stuff, you take all these ideas and move them out into 3 dimensions. Right? Calculus also takes a look at area problems. Now, without calculus, the area problem was reduced down to geometry. If you could look at a shape and recognize a geometric figure in there, or maybe the sum of several geometric figures, you could calculate the area of those pieces, those geometric pieces, rectangles and triangles and circles and things like that, and find area. But calculus says, what if we want to find the area of something that isn't geometry? What if we want to find the area of something where that top of it isn't a straight edge, but it's a curved edge? How do I do that? Geometry fails me. And because geometry fails me, I need more powerful mathematics, and the more powerful mathematics is calculus. Okay? If you took a physics class, you might have taken a look at the idea of work. But without calculus, the work that you ever calculated was always a constant force. You're pushing a block with 2 newtons of force. How much work is done? In calculus, we can talk about a variable force. A force that starts out strong and gets weaker, or a force that starts out weak and gets stronger. Right? Without calculus, you may have done some centers of geometric shapes. You might have found the middle, in a sense, a balance point, if you will, of that rectangle. But what was required was that this whole thing was made out of the same material, the same thickness, the same density all over. With calculus, we don't need that. And we can find centroids of regions. Now you might be asking, why would I ever do that? Well, the centroid is the place where you put the axle if you want to spin it so it doesn't wobble. Right? In algebra, you took a look at lengths of line segments. You remember you had a distance formula to find lengths of line segments. You said that d was equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. But you were limited to certain geometric figures. Like it had to be a line segment, or it could be part of a circle. Because you knew how to do that, you could find a arc on a circle. But calculus says, what if it's going to wiggle? How are we going to find that? So I hope what you're seeing here is what we're talking about is making changes to the math that we already know how to do and just making it more complicated. Instead of finding a simple geometric shapes surface area, what's a complicated geometric shapes surface area? Instead of finding the volume of a simple geometric shape, what's the volume of a complicated geometric shape? Instead of finding the mass of a solid of constant density, what if the density is variable? What if the density changes throughout the material? How do you find the mass of it then? How can you predict that mass? And then when you get into this, you get deeper into this, you can talk about finite series and infinite series, which have applications in a wide variety of fields. Right? Now, here's the original problem that started calculus, or started one part, differential calculus. Mathematicians of the time wanted to know how to find the tangent line equation to a known curve at a known point. And so basically this is where half of calculus, differential calculus, started. Okay? Almost all mathematics was born out of a need for something. And for whatever reason, they needed to know this. Okay? The entire field of probability theory, where we calculate the chance of something happening and make predictions, that was all built out of guys wanting to know how to gamble better. Okay? And so people studied the math and studied the math and studied the math, and then essentially new mathematics was developed. This was the new mathematics. They wanted to know how to find the equation of that. Okay? Now the other side of calculus, integral calculus, which we'll take a look at the end of the semester. So we'll take a look at this around Thanksgiving time. Okay? Ask this question: how do I find the area under a curve? How do I find the area bounded by a curve? Geometry fails me, because that's not a circle or a square or a triangle or any of those geometric shapes that I have a formula for. So how do I find it? And that was what the other half of calculus worked on. Right? So basically what's going to happen is this entire semester we are going to be working with problems where we are going to have essentially at the end some real world application, some real world component, and are going to require you to do some problem solving. Right? Now, what I would like to is just remind you of the problem solving approach. Okay? So when we get to the word problems, the problem solving approach can basically be broken down into 4 steps. Step 1, make sure you actually understand the question. What are the givens and what are you being asked to find? Okay? This is where you take a look at what is told to you to be true and what you are asked to find. Essentially, that asked to find is where you identify your variables. The second step in the problem solving process is to come up with some sort of a plan. Okay? Figure out what is you going to do. Hey, is this problem like a similar one that you've done before? Do I need to draw a picture? Am I going to need some sort of technology? Should I look for a pattern and then use that pattern to solve this? Okay. Third step in the problem solving process is to actually do the thing that you just laid out. Complete the plan. Okay. Verbalize the answer. Okay. Remember that if a variable is not defined in the problem, and you define it, if you say x is going to be the length of this thing, the answer can't be x is 3.5, because that doesn't tell me anything, because I don't know what x is. You made it up. So it's better to write it out as a full, complete answer, to say the area of the region, or the length of the side, or whatever it is you decide your variable is good for. Okay? And then, of course, the last step, the one that people tend to have trouble with. Look back, check your work, make sure that your answer makes sense. Okay? If your job is to find out the length of the side of a box, and you know that the volume of the box needs to be 100 meters, or 100 cubic meters, and you get an answer of 0.4 meters, does that make sense? Could you visualize a box that was that size and had the right volume? Okay? So that's your problem solving approach. So essentially, what section 2.1 is just an overview. There's no homework from section 2.1 because there's not really much we can do here. You notice we actually didn't do any math. It's just this is what you should be looking forward to seeing throughout the rest of the semester. We're going to find limits. We're going to find slopes of curves, slopes of tangent lines. We're going to find instantaneous rates of change. We're going to find area under a curve. We're going to find tangent line problem answers, and we're going to find area problem answers, and then applications of those. All right, the next video will be section 2.2, where we're actually going to start doing new mathematics. We're going to start taking a look at the idea of a limit.